Hey everyone, and welcome to today's Explainer. We've got an absolutely thrilling topic today. We are going to dive headfirst into a massive, high-speed computational revolution that is completely reshaping the world of chemistry as we know it, accelerated molecular discovery. We're going to explore exactly how the intersection of chemistry, artificial intelligence, and physics is allowing scientists to map out brand new materials faster than ever before in human history.
Okay, let's dive into this. Here's our roadmap for today's explainer. First, we'll look at the speed of molecular discovery. Second, finding the energy path. Third, the machine learning turbocharge. Fourth, the new frontier, INRs. And finally, number 5, accelerating tomorrow's materials. Now, I know some of this might sound a bit intense, but don't worry. We're going to break these complex concepts down into a really logical, step-by-step evolutionary sequence. All right, let's kick things off with Section 1, the speed of molecular discovery.
So, historically, the absolute biggest bottleneck holding back molecular chemistry has been the sheer amount of time required for traditional quantum calculations, specifically something called DFT. Now, DFT calculations are incredibly precise, but doing just one single calculation can take days. It's literally like watching paint dry, and it completely stalls the momentum of an entire research project. But by bringing in machine learning interatomic potentials, we can predict those exact same molecular energies in seconds. Let that sink in. It's a mind-blowing leap from waiting days for a computer to crunch numbers to getting near instantaneous results. That brings us perfectly to Section 2, finding the energy path. Right, so before AI could swoop in and turbocharge the process, scientists first had to figure out how to computationally map the actual journey of a chemical reaction. They couldn't just guess. They relied on a foundational tool called the nudged elastic band, or NEB technique. Basically, NEB identifies the minimum energy path between different molecular states. Because, molecules don't just teleport from being reactants to being products. They actually have to travel across an invisible energetic landscape, and NEB maps out this transition using a specialized sequence of images. To really visualize how this works computationally, I want you to imagine dropping a string of beads onto a really rugged, mountainous physical terrain. What happens? Gravity naturally pulls that string right down into the lowest valley, connecting 2 points, right? Well, NEB does the exact same thing mathematically. It places a chain of molecular images between the reactants and the products, slowly nudges them across the molecular energy landscape, and optimizes them to find the absolute lowest energy path required to make the reaction happen. Okay, moving right along to Section 3, the machine learning turbocharge. Now, running those traditional calculations for every single bead along that path, that takes an enormous amount of time. And that is exactly where we introduce AI to turbocharge the whole thing. Machine learning force fields and graph neural networks predict molecular energies with remarkable speed. This is a real game changer. Instead of painstakingly calculating the complex physics from scratch every single time, these models are scanning molecular structures directly at totally unprecedented speeds. Now, what's really interesting about this breakdown is how advanced models like SNET, for example, actually pull this off. They achieve this blazing speed because they don't just calculate, they actually learn. By taking in inputs from massive datasets that contain millions of molecular configurations, the AI learns the underlying physical rules of the molecules. And because it fundamentally understands the mechanics, its output totally bypasses those days-long calculations we talked about earlier. It just predicts the energies in seconds. Which leads us to Section 4, the new frontier, INRs. So, what's next? The absolute cutting-edge, newest evolution in this whole process is the use of implicit neural representations, or INRs. Instead of just looking at individual, isolated points in a reaction, INRs are this brilliant digital innovation that maps complex chemical reactions as smooth, continuous mathematical functions. This is quite literally the frontier of how we model chemical mechanisms today. To really lock this in, let's contrast it with the older method. The traditional EME method we looked at is a discrete sequence of individual molecular images. Think of it like a flipbook. It works, you can see the animation, but it's clunky and you are strictly limited to the specific frames you drew. INRs, on the other hand, act like a smooth, continuous, high-definition video. Because they use a continuous mathematical function to represent the entire path, there are absolutely no gaps. It's a seamless flow.
So the crucial point here is that because ion errors create this continuous mapping, they allow the AI to instantly estimate transition states, yes, even for highly complex multi-step mechanisms. By abandoning those clunky discrete beads and utilizing a continuous function, the AI instantly identifies the most critical, energy-heavy moments of a chemical reaction. It entirely removes those old multi-step bottlenecks.
And finally, we arrive at Section 5, Accelerating Tomorrow's Materials. We really need to talk about why all of this matters outside the lab. The integration of AI with specialized pathfinding algorithms like NEB and INRs, it isn't just some abstract math trick. By finally overcoming those traditional time constraints, we're enabling the rapid discovery of chemical mechanisms. This computational synergy is exactly how we are going to accelerate the development of new, genuinely life-changing materials. We're talking about better batteries, more effective pharmaceuticals, and stronger sustainable plastics, all developed in just a fraction of the time it used to take. Think about the journey we just took. We've gone from waiting days for a single calculation, to predicting energies in seconds, to now completely mapping continuous reactions instantly. With artificial intelligence now possessing the power to effortlessly map these complex chemical reactions, you really have to wonder, what revolutionary new materials will we discover tomorrow? Thanks so much for joining me on this explainer, and definitely keep exploring this incredible frontier.